Good morning, everybody. Today is Codeforces round 671. It's a Div2 round, and I'm going to be competing live. If you're interested in solutions, I'll have those at the end of the video to all the problems that I know how to solve, at least. And a little bit loud. There's a semi-truck outside my window. But yeah, we'll see. Good luck, have fun to everyone competing. I guess before we start, one thing I wanted to mention is I've used Eclipse for a very long time, but I'm considering switching to VS Code as a new editor of choice. So if you have any strong opinions on that, let me know. But we'll see. Yeah, I'm considering doing it. Not for today, though. Today we'll just compete. So let's see what the problems are. Problem A, digit game. Everyone knows that agents in Valorant decide who will play as attackers, who will be defenders. Raze and Breach have decided to play team matches of the digit game. In each of the team matches of the digit game, a positive integer is generated, has n digits. You can turn an agent and choose any unmarked digit and mark it. You can choose digits in odd positions, but cannot choose digits in even positions. You can choose digits on... Wait. Okay, the other person can choose on even, but not on odd. The match ends when there is only one unmarked digit left. If the last digit is odd... Oh my goodness, what? We proved that before the end of the match, each agent has an ability to make a turn. Is n even or something? Oh no, it doesn't matter because the first person is odd. Odd positions, yeah, okay. Each agent will win if both of them want to play optimally. So in this case, there is a 2. So how does this work? When there's one digit left, they should name these Alice or Bob at least. First and second would work as well. Raze starts. So Raze is Alice. Okay, so if the last digit is odd, Alice wins. So Alice wants the remaining digit to be odd. So you print 2. Because last digit is even. Okay, then if it's odd, then 2 wins. Okay. So yeah, in this example, why does 2 win? This doesn't seem as obvious as the problem A should be, but why does player 2 win? So nine is the only odd one. Let's move on to problem B. Well, what does the scoreboard say? How many solves does this have? Okay, it is actually hard. Man, this is ooh. Coordinators are not gonna hear the end of this one in the comments. This is a hard problem A. Yeah, because usually I'm pretty good at game theory from my experience. So I don't see, it's not obvious to me at least. Maybe it's some pigeonhole principle. So if you've got 1, 2, I mean, all that matters is the parity, right? Can the digits be 0? Without leading zeros, but it might have, can it have leading zeros intermittently? Oh, you mark it, you don't delete it. Got it. Okay. Yeah, so this is not too bad. So now, whoever moves last chooses whether it's odd or even. So you just count the parity of n that the person chooses, and then if that person has one of what they want, then they win. Yeah, okay. So let's do this. So int n leave this. That's one of the reasons I'm considering switching to VS Code. Okay, so if n mod 2 is 0, then Alice chooses who wins. Otherwise, Bob chooses. Let's get the array. So if Alice is going to choose who wins, we care about the things at odd positions. So wins or equals 8i mod 2 is not equal to 0, because Alice wants it to be odd. In this case, Bob wants it to start at 1, increment by 2, and Bob wants it to be equal to 0. So now, we win, player 1 wins, otherwise player 2 wins. And this one is backwards. Bob can force a win, then Bob does, otherwise Alice wins. What? Oh, yeah, okay. Array line equals so this is 8i minus the character 0. Yeah, okay. So cool problem, I guess. Kind of boring, although I don't have it right. Why is that? There's just a 2. That means the parity is even, so Bob chooses the winner. Yeah. Now the question is, does Bob have something who wins? Bob does. Oh, yeah, wait a minute. Okay, so it's also possible if Alice has, wait, if the, all right, my solution's wrong. Hold on a minute. 102. Let's pause and figure out why we're wrong. 102. So these are both Alice's and this is Bob's. So Alice deletes 1 and Bob deletes 1, right? So this one doesn't matter because it gets deleted. And Alice wants to delete this one, so Alice wins. I say it's a 1, but I print 2. Why is that? Check position 1, position 2, one of them is odd. Am I an idiot here? What? Character 1 minus character 2 is 1. Mod 2 is not equal to 0. If wins is true, print 1. What the heck? Oh, duh. Okay. The answer to that is 1. Okay, so that seems fine. Let's double check. Yeah, let's just try it at least. Because this, that should not have taken me 11 minutes. Not even close, man. Not even close. Alright, anyway. Jeff is tired of destroying the town. She wants to have a rest. Jet. She likes high places. That's why, for having a rest, she wants to... Okay. Find a high place. Surprised this got approved as a problem statement. She is a squared figure that consists of squares. Oh, it's a staircase, yep. Okay, I think I know what a staircase is. A staircase with n stairs is called... Lowest stair of the staircase must all be the same row. Okay. Staircase with n cells is called nice if it may be covered by n disjoint squares made of cells. This is how a nice covered staircase with 7 stairs looks. Find the maximal number of different staircases that can be built using no more than x cells in total. This is a Div2 round, man? Yikes. Okay. Yeah, so clearly not that many. If we can build one staircase, or I guess we just try all of them, maybe. So if you place I guess let's see. So if you want a 1 by 1, you have this. If you want a 2, then you have this. That's your only choice. If you want a staircase of size 3, then you can do this. And then what about 4? Then you have to do a 2 by 2, right? So you place this and now you have these two. So yeah, okay, so size of x will be, it's like recursive, so either if x mod 2 is 0, then we want takes 1 plus 2 times size of x over 2. Am I missing something? Seems like it might be quite big. Why is this answer only 30? Size 6, you can build what? Wait, what is a nice staircase? Staircase is nice and may be covered with n disjoint squares made of cells. Oh, so yeah, so we need to place one square for each cell. So that means we have to start something in each corner, right? So we need one here, 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 here. Which means this needs to be one big. This needs to be two big. This needs to be one big. This needs to be 4 big. So 1, 2, 1, 4, 1, 2, 1. I've seen this pattern before actually. It came up in an earlier problem. So what's the problem now? What are they asking me? How many different nice staircases can be built using at most this many? So you've got 1. You've got 1, 2, 1. Then you have 1, 2, 1, 4, 1, 2, 1. So these numbers are 1, 1 times 2 plus 1. Whatever this number is, times 2 plus 1. Okay. So long x equals the next long. Long count, I guess int count equals 0, long val equals 1. Well, val is less than or equal to x, then count plus plus. Val equals val times 2 plus 1. And then sys out the count. Nope, not even close. Okay, 6 doesn't work. Why not? 6, you're telling me the answer is 1, 4? Wait, what is the problem? It can be built simultaneously? Oh, different nice staircases. Got it. Okay. Fine. Then x minus equals val. Is that what they want? That still isn't right. So we can do a 1, and we can do a 1, 2, 1. Why can we not do both of these? We can. Yeah. Oh, and the number of cells is important? Okay, fine, dude. Not the number of squares. Fine. Power equals 2 initially. Okay, so val equals the number of squares. Okay, so this plus power, and then power times equals 2. I think this is fine. Ooh. Yeah, this is wrong. So this needs to be power times power. That looks right. 1, 2, 1, etc. Okay. Well, let's get this over with. You know, for how disastrous this contest has been going for me so far, it's still pretty recoverable, I'd say. We've only burned 20 minutes on it, right? 10 minutes on A, 10 minutes on B. So, like, you know, it's not the end of the world. Obviously, in Codeforces, the minutes in the beginning matter, like, the most. But, yeah, and that was, like, pretty horrific. But, yeah, it's not the end of the world, I'd say. And also, this is definitely a hard contest. Like, I'm certainly not doing well, but, like, I don't know, I'm not losing to too many cyans. So, yeah. Let's do C. Killjoy, a new agent called Killjoy, has invented a virus, COVID 2069, that infects accounts on Codeforces. Each account has a rating described by an integer. Killjoy's account has already been infected and has a rating equal to X. Its rating is constant. There are n accounts except hers, numbered 1 to n. Initially AI, any affected account instantly affects any unaffected account if their ratings are equal. This can happen at the beginning, before any rating changes, or after each contest. If an account is infected, it cannot be healed. Contests are regularly held on Codeforces. In each contest, any of these n accounts can participate. Killjoy can't. After each contest, the ratings are changed in the following way. Each participant's rating is changed by an integer, but the sum of all changes must be 0. The new ratings can be any integer. Find the minimal amount of contests needed to infect all accounts. You can choose which accounts will participate. Each rating is changed by an integer, I see. You can choose which accounts will participate in each contest and how their ratings will change. It can be proven that all accounts can be affected by some finite number of contests. Is that true? Oh, Killjoy's rating is constant. Yeah, okay, so it is true. Interesting problem. Let's think about it for a minute. We've got whatever our number is, so let's look at a sample, maybe that might be helpful. So our rating is 2, and the accounts are 68 and 70. Or wait, no, what is our rating is 69. Yeah, okay. So we're at 69, and then there's 68 and 70. So in one move, we can combine these, like these can all be together. It's always possible in 2 turns, right? That's the secret. Yeah. So if they, yeah, so it's just 3 cases. So is it possible in 1 turn is the only question they want to ask, I think, right? Because you can always do it in 2. So let's just try that. Good. So first we're given n, then we're given our rating, not too big. Then we're given everything else. Okay, so Boolean all equal equals true. So if all equal, then sys out 0 and continue, because then everyone will be affected instantly. Otherwise, we can get everyone equal to us except for one person. So now we just care about this last person. So int, or I guess long sum equals 0 for int I in A. Sum plus equals I minus hours. Now if, well, I guess now just sys out sum mod 2 is 0. If it is 0, that means we can do this in one turn, otherwise it'll take 2. But we can always do it in 2. Really? You're telling me this takes 2 turns? Oh, what am I doing? Sum mod 2, just sum. Yikes. 102, yeah, okay. How many test cases? Only 100, seems fine. I'm pretty sure this is right. But bounds are unusually small, which sketches me out.
Problem Sega, wrong answer, test 2, sir.
Yeah, okay, so the question is, why are bounds so small? Is it not possible in 2 steps always? Maybe I just don't understand the question. His rating is constant. Okay. Any infected account instantly infects any unaffected account if their ratings are equal. Okay, in each contest you have n accounts that can participate. Rating changed in some way is changed by an integer, but the sum of all changes must be 0. New ratings can be any integer. They're all equal to ours. Print 0. I have no idea what the break case could be. You can, if you have some numbers, we want to make all of these equal to 5. Then we can turn this into 5, we can turn this into 5, and we can turn this into something else. Then the next turn we can turn this into 5. Oh, wait, no, that's fine. Yeah, that breaks it, okay. So if we have, what if we have 3, 4, and 5 turned into 5? That's the break case. Okay, I got. So 3, 4, 5 with 1 test case, and then we start at 5. The answer to this is just 1. What did I say, 2? Boolean start special equals false. there's the answer. On to D. Let's go for D2 because we've got enough time. Today is Sage's birthday. She will go shopping to buy ice spheres. My
Answer is either problem C.
My ICPC team was called Sage, not this year, but the previous year. And also my Microsoft interviewer's name. When I was interviewing for an internship at Microsoft, my interviewer's name was Sage. So it is a real name. It's also a spice. All n ice spheres are placed in a row numbered 1 to n, left to right. Each ice sphere has a positive integer price. In this version, prices can be equal. An ice sphere is cheap only if it costs strictly less than the two neighboring spheres. The nearest, what is TP? Okay. The nearest TP, oh, is this nearest to? Nearest to the left, and the nearest to the right. Okay, thank you. The leftmost and rightmost ice spheres are not cheap. She will choose all of the, oh, got it, yeah. She'll choose all ice spheres and buy only them. Choose the cheap ones. Okay, got it. You can visit the shop before Sage and reorder the ice spheres in any way you wish. Find out the maximum number of ice spheres she can buy and show how the ice spheres should be reordered. So, wait, what? In the easy version, is the answer not always it doesn't matter? Oh, I guess just put the biggest things in the end. Yeah. Wait. Oh, she only goes once? She doesn't go repeatedly? Oh, okay. Yeah, so the easy one is easy. The hard one, we're going to want to use a prefix of these things. Okay. So say we've got some numbers like 1, 2, 3, 3, 4, 4, 4, 4, maybe some more 4s. Then we'll put a 1 here, a 2 here, a 3 here, and a 4 here. Well, I guess let's do this. So we've got these are the positions that count. We will label all of these. And then we want to keep skipping positions as long as we need to in order to place something here. So we get to the 4, then we place a 4 here, then we place a 4 here, then a 4 here. Then we can't place a 4 in order to beat this, but we place the last thing here, and then we just like fill these all with -1. Then we count how many work at the end. Okay, so we can do that. The easy version, well, I guess we'll just do the hard version anyway. We won't even worry about it. So we have this sorted array. Very good. Now, yeah, we need to place things. So we'll have an array deck. Or I guess, how do we want this to work? Yeah, so first we place the first thing bigger than 1. Oh, do we want these all to be candidates or not? Does it not matter? Yeah, we might as well have them all be candidates because it's less than half. So, okay, so we'll have array list of candidates, maybe? What have I done to my cursor? Let's just restart Eclipse real quick because it's going to bother me. Yeah, so we'll have an array list of candidates for each of the positions, and then we can iterate through these. Oh, I guess it might be easier to go from the end. So we'll keep deleting these as long as they match the biggest. Then we can place things starting here. We might not be fine though. Yeah, we're not going to be fine. So I think we have to go left to right actually. Yeah. So I equals 0. I is less than n over 2. Okay, so this isn't actually right though, because if n is 4, we don't want to add 2 things, we just want to add 1. N is 3, we want to add 1 thing. So now we have all of our candidates. So now for this, I is less than n, I plus plus. I guess we'll just do a while true here, and then worry about the logic in a minute. So we'll make this an array deck, probably. And then we need to do the sweep here. So Boolean have 1 is false. Okay. So yeah, okay. So now if I is equal to n minus 1, then break. Otherwise I plus plus. So now we need to say, like, if we can't make it, so there's this case left. Otherwise, we need to say, can we place here? When is that true? So while 8i is equal to candidates dot peak first and I plus plus, I is less than n, and that. Now, if I is equal to n, There's one thing, otherwise there's this other. So if I is less than n, we can place this thing here. We might as well do it. So now ans plus plus. Otherwise, if have 1, then ans plus plus. In this case, have 1 equals true. Oh man, we also need we need to extract it. I forgot about that. And I'm not even getting the right answer. Silly me. Okay. These skipped things will happen here. Okay, so then at the end, extracted dot add all the skipped ones. In this case, skipped dot add 8i. If we have one. We want to add these in reverse order. Oh, it shouldn't even matter. Yeah, because we'll pass it right here. Okay. There's definitely an easier way of looking at this problem than what I'm doing now, but I think this ends up working. Okay, well this is true. If I equals 1, if we have 1, increment it. And now, regardless, for or I guess while not candidates dot is empty, then candidates dot remove first, and then skipped dot add that. So remove all of the candidates we don't get to. Okay, otherwise, first we pull extracted. So extracted dot add 8i. And then candidates or extracted dot add the thing we just removed. So you can do 3, 1, 4, 2. Yeah, okay. and not candidates dot is empty. So what if the candidates is empty? Then for, I guess, yeah, then do this. Oh my goodness, so messy. This needs to come first. Okay, 3, so we get this one, and then we're out of luck because we never added the 5. So skip that, add this. How do we break? In this case, we add all the candidates. It's this one, I think. This adds the rest of candidates. We also need to add the rest of the positions. Or when does it break? It breaks in this case. Because we're out of candidates, we just place the 2. So this shouldn't be this. This should be, well, I is less than n. Then skip dot add a at I plus plus. So we get the 1, we get the 2, we get the 2. Okay, let's try some other stuff. So just 1, we get 0, and it's 1. 2, they're both 1, we get 0. 3, they're all 1. Get 0. Okay, what about 3, 1, 2, 2? And we get the 1. Okay. 3, 1, 1, 2. That's a problem. Okay, so okay, we have an issue here. The issue is that first issue is I can't read my code. The bigger issue is that in this case, candidates is empty. No, candidates isn't empty. So we place this 1 in the 2. We say we have 1. We add this. But we have an issue still. So the issue is that This is too small. Then we increment 1 here. Oh wait, why are we incrementing this? Yeah, I think that's fine though. Okay. 3, 1, 1, 2 is what we just tried. Now 3, 1, 2, 2. That shouldn't be 0, that should be 1. Place the 2, 1. Now when we get to the next thing, candidates.isEmpty is true. Okay, it's a little bit simpler. Okay, so yeah, so this commentary is kind of a bit boring because I'm trying to figure out what on earth I'm doing wrong. And the logic is like very complex, and there's probably a better way of doing this. But I guess this is what's gonna happen. So if the candidates list isn't empty, yeah, so what's going on here? So we've got several things, we've got like all of our candidates. This means we run out of like big items. This is we run out of candidates. If you do run out of candidates, so yeah, what's the break case here? The break case is first we do this. We don't increment because we're here. And now we see this next thing. So now when we see this next thing, if we're out of candidates, if have 1, then we want to increment. If you run out of big items though, then you count for the person before you only if you're not also out of candidates. But if you were out of both, then this would get triggered. Okay, so now the other one is 3, 1, 1, 2. Gives me 0. Then this one should give me 3. That seems right. I guess let's do print writer real quick. Oof. Darn it. Darn it. Good thing I checked. Yeah, I think that's fine. Okay. Submit to D1, I guess. Here's the question. Do I submit to D2? No, I don't, because it's running. So I wait to see if it's wrong so I don't double burn penalty. Okay, now I submit to D2.
Right answer is either properly done.
And now we check whether I handle things being different correctly.
Right answer is either problem D2.
That feels like it might have a lot of hacks because it feels like there are lots of cases with it. But alright. How are standings looking? Not terrible, not terrible. I'm in 400th place, losing to blues, but that's fine. Nothing out of the ordinary, I'd say. Just kidding, just kidding. I don't like losing to blues. Let's solve problem E and fix that. What do you say? An agent called Cipher. Man, there's so many agents, and like, I don't know. I'm not really a fan of these types of flavor text because it's just like several paragraphs of stuff that doesn't help us. Anyway, an agent called Cipher is decrypting a message that contains a composite number n. All divisors of n which are greater than 1 are placed in a circle. So we have a circle of at least 3 numbers. Now you can choose the initial order of the numbers between. Do we have this number? Composite number n. Got it. What were we saying here? Wait, what? How could that possibly happen? Total number of advisors of n. Of course they won't. The number of test cases is only 100. You're telling me there's some number with 10 to the third? Well, I don't know, maybe there is. Whatever. Doesn't matter. Jeez. In one move, you can choose 2 adjacent numbers in a circle and insert their LCM between them. Do that as many times as needed. The message is decrypted if every 2 adjacent numbers are not coprime. Hang on. Are not coprime? If they share some LCM? Okay, got it. Oh, all divisors are greater than 1, so you might only have 2 things in the circle. I see. Message is decrypted if every adjacent number are not coprime. Note that for such constraints, it's always possible to decrypt the message. Find the minimum number of moves you can decrypt the message, and show the initial order. So for 6, you want 2, 3, 6. And then you need to do 1 operation, because there's 1 pair. For 4, you have 2 and 4, and that's fine. For 30, you can do 0. Okay. So this is kind of messy. I don't know if I like this problem. This whole thing is kind of messy. It seems like just messy constructions. And F doesn't have any solves yet, right? F doesn't have many solves. So this is the one to go after. So the idea, I think, is we just need to case it out. So if you have a to the 1, well, a to the 1, yeah, let's say you have a to the 1, b to the 3, maybe. So the numbers you need are going to be a to the 1, a to the 1, b to the 0, or a to the 1, b to the 1, a to the 1, b, two, let's just say a to the 1, b2, maybe. So b0, and then you also have a0, b0, a0, b1, a0, b2. So this one we don't actually have to care about. But now for this, we want to connect these things. So we can connect these two, we can connect these two. We can connect anything with a B in it, and also anything with an A in it. So we can connect any pair of these, like this is a click. This is also a click, because it has an A. Now this is like some section, so these are like very free, these two things, because you can connect them to either an A or a B. These ones are fine because everything has to have a degree of 2, right? So you can enter one side and leave the other. But now you have issues here because this only has 1. So we need to prime factorize this. Then the answer will be for everything that has this 1 power, we'll need at least one thing to leave it. So answer is like number of things, number of prime factors equal to 1. Now we need a construction to prove that. So let's say a to the 1, b to the 1, c to the 2 or something. So what do we do here? Well, we're going to have a to the 1, and then we'll have a to the 1, b0, c, c0. We'll also have b to the 1, a0. Maybe I should just draw them out in like a regular form. Okay, then we have, I guess I can just stop, I'll just do 0, 0, 0, 0, 0, 1, 0, 0, 2. Then we have 0, 1, 0, 0, 1, 1, 0, 1, 2.
Always a pleasure hearing you work, sir.
We have company.
Understood, sir.
And finally, okay, so now we need a way of traversing this. So we can go down like this. Or this one doesn't exist. First step we can ignore. So we always add all of these edges. It doesn't hurt. And after adding all of the edges, now these are just single nodes. So now you just have a single node with one fewer number of elements in it. So initially this was like a tuple of length 3. Now it's a tuple of length 2. So after doing this, now we have 0, 0, 0, 1, 1, 0, and 1, 1. Oh, now we need this thing where it like differs in as few places as possible or something. Yeah. So we need some clean way of traversing through this, which I think would be this here. We need 0, 0. Well, we don't have 0, 0 ever. So I guess this is a different case now, because we didn't start with it. If we had added this anyway, it would just add 2 to our answer, right? So we can just subtract 2 and then remove it. Yeah, maybe that's helpful to think about then. So once we're left with all zeros and ones, how do we handle this? We need some way of doing this in a fast way. So we're going to lose points for this one and also for this one. I suppose we can reorder it though, right? So if this is what they look like, let's order them by this first column. So now we have 0, 0, 0, 1, and then we have 1, 0, and 1, 1. We can imagine taking this edge. I think. Also imagine taking this edge. Then we can combine these two. Go like that. So this is like a hypercube traversal, basically. We just want to traverse this hypercube. Yeah, it's an easy thing to do. Who doesn't enjoy traversing hypercubes in their free time? Okay, so what is this going to look like when we implement it? The idea is that we pick some dimension, and then we order everything on that dimension. well, okay, first then we solve everything else. Like solve removing that dimension. That will give us each of these loops. Now once we have the loops, we go like this, maybe? And then at the end, we connect whatever is left over to the beginning. Now we have one final loop. This might not work though. Reason for that being this connection from the beginning to the end is sketchy. So what if we have 2, 2? We have 0, 1, 2. If we just have a 2, then we'll have this 0 to 1 to 2. Okay. So now we have 0 with a 0 to 1 to 2. And then we have a 1 with a 0 to 1 to 2. And then we have a 2 with a 0 to 1 to 2. Okay, so we can connect these two for free. That's fine. We can't actually make this connection though, so we can do that. Then we can connect this to that. And also these two. We're also allowed to do this since we have one of them. Yeah, okay. Alright, that's kind of annoying. So we're gonna need like some solve where we have 0, like we know whether we have 0 prefixes. And then we also know whether this thing, because if we don't have 0 prefixes, we're allowed to add this edge. Yeah, we also want to know which digit we're on. And this will place each possible copy of the digit and move to the next digit. When do we have to pay an additional cost? That is, we have to pay the cost if we're placing a 0 and we had a 0 prefix. But this never actually happens. Oh, can we just count up? Oh, am I an idiot? Ah, my goodness. What am I doing? 0, 0, 0, 0, 0, 1, 0, 0, 2, 0, 3. No, we don't want to count up. Do we? Yeah, this is not going to work. because here we have a 0, 1, 0. So we can actually make this jump. All right, how do we do this in a better way then? It is a lot like traversing a hypercube. That has almost all of the edges, but just not certain edges. Like you don't have an edge to something if you're all zeros for it. We only need to handle one special type of move, which is the, like just the zeros are really important. There's like a certain type of code, something code, I think. I want to say it's like red code or black code or something, where it's like a series of numbers. It's like I think 1, 3, 2 or something, where like 0, 1, 3, 2 would be an example, where it uses like all of the numbers 0 to 2 to the n minus 1. And then they differ by 1 in each position. Like they have 1 bit that differs. So this is the 1 bit, this is the 2 bit, this is the 1 bit that differ. There's some way of doing that, which feels a lot like what we want here, except it's less restricted because, yeah, there's a better way of doing it. Maybe let's start with the powers that matter. Well, we haven't done that yet. We haven't even... We've got 0, 0, 1, 0, 2, 0, 0, 0, 1, 1. This is 1, 0, 1, 1, 1, 2. So we need to come up with a way of traversing this even. How do you do that? We can skip this, but now everything else needs to be reachable. So we can add this edge here. We can add these edges here. We can add these edges here. Now we can go like this. Yeah, because it's sure an A. Can we always add this edge? No, I drew this wrong. We can add it in this case, but we can't always. The other case would be if we just add one more row. We have 3, 0, 3, 1, and 3, 2. Then if we add edges like this, we're not allowed to add this edge here because these actually are coprime. So in this case, maybe, so many cases. Okay, maybe there's a better way of doing this. Which we can use based on the fact that the number of factors will be small. The number of prime factors is tiny. Yeah. Traveling salesman DP. Sounds like it. So we have log n prime factors. That's actually not going to be good, right? Because we really have cube root. We've ended the 1/3 factors. How many masks of prime factors do we have? That's the real question. It's going to be pretty slow, I bet. Two times 3 times 5 times 7 times 13 is the next prime, times 17. Times 19 times 23 times 27. That's as big as we're gonna get. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So it's 2 to the 9 nodes. We can't do a TSP on that many nodes. So we have to be smarter. Alright, I'm gonna go to the bathroom and think about it for a bit. Yeah, so I think maybe we'll read F, take a quick break from E, because I spent a lot of time on it and I'm not really getting anywhere. After he reaches an arbitrary detachment. Okay, so you got a bunch of points. You want to visit all the points? Okay, find the minimal time to be able to visit all of these things. So you can only move up, down, left, or right between two things, which is a pretty significant constraint. Does that make the graph bipartite? No, it is not bipartite, because you can have an odd cycle. It does feel kind of flowy though, which is interesting. There are also a linear number of edges that exist in the graph. So the graph is pretty small. You also get to add one more, which is a bit odd. But you can also, like, it can be different too. For instance, you can have something that's like, if you have this here, it's not obvious, but this is possible. If you put something in the middle, then you can go like this. Is this the sample actually? It is a sample. The answer is 100. It takes 100 time to get all of them? That doesn't seem right. Oh yeah, that is right. Because we're only looking for the maximum distance, not anything else. So we just care about the maximum value in this graph in order to get them all connected. And also we only get one of these. So we can binary search it. But in addition to binary searching it, we just need to check, or we still need to check, is it possible for a given value? For a given distance? So we can do a disjoint set to merge some stuff. And now we've got these components. We can merge all of them with this. It's kind of weird. Also, the components can be in odd shapes. Like they might be like this or something. They might be all over the place. But if we place one thing, we can combine. Oh, you can only combine two. You can join two components. So we need 2 of these things. Yeah, you need two groups at the end. Once you've got the 2 groups, then you can join them. Like if you have 2 groups, then you can do an n squared to check. So our runtime is going to be n squared log n times Ackerman. Nah, not times Ackerman. Just n squared times log. Yeah, let's just double check this. Because like competition wise, we're gonna get F, we're not gonna get E. That's just how it's gonna work out, I think. Unless E winds up being really easy and I'm just not seeing it. So we binary search the answer. For a given answer, we have some things. And then we have 2 points left. And the points are gonna differ like this, so we'll brute force these 2 points at the end. If there are more than 3 components, then, oh, it might still be possible. Yeah, okay, that's kind of weird. It might be possible. Okay, might be possible. Might be possible. But then, if you've got something like this, ultimately we're gonna need to join 2 things like this. So either they're gonna need to be 2 things that are at different orientations, or 2 things at the same orientation. If they're at different orientations, like this, then the point is forced, so we just need to check this one as well. And also this one here. If they're at the same orientation, then it can only be these 2, so we just need to check the previous distance. Ugh, kind of messy. Well, we might as well just code it. So we're gonna need to compress these. Okay, yeah, something like this. So we'll need the number of points. And then static void compress. So tree set integer x's and y's. So put x to x map that size, and then same thing for the y map. Now for vec v in points, v dot x equals x map dot get v dot ox, and then same thing for y's. Okay, so now we've compressed our points. We should probably have an array for points on each integer. Or maybe we can just make it 2D grid. Well, what do we want? We just want the next point in each direction. So now, if v dot your, okay, so if v dot x equals u dot x, then directions will be up, right, down, left. So if indirector equals null, then return true. Boolean. Public int Manhattan distance to some vec O will return math.abs of x minus O.x plus math.abs of y minus O.y. Otherwise, return Manhattan distance to O less than the Manhattan distance to indirector. So if v dot better in the direction of up, compare it to u, then v dot indir at 0 equals u. Direction down is direction 2. Otherwise, what are these errors? Come on, what's my problem? If v dot y equals u dot y, we've got some stuff here. So for the x's, if they're different, if the first one's smaller, then this is direction 3. Otherwise it's direction 1. Okay, so now we have the best in all 4 directions. int min ants will be, well, I guess we should just try this. We just need a method for this, static boolean possible for all the points. And then the distance, right? And dist. So we need our disjoint set here. Disjoint set dj to disjoint set. ID. This dot ID equals ID. So initially we have this size. So now for vec v in points. Oh wait, do we need restorable disjoint set? Yeah, I do. Okay, so now dj.save here, and then dj.restore. Do this for every pair, not for these. Okay, so for int or vec o in v dot endure, if o is null, continue. Otherwise, dj.union v.id with the other things ID. Oh, we care if the distance is small enough though. So if v.manhattan to o is less than or equal to this dis, then union them. Okay, so now we have this. So now for vec v in points, for vec o in points, oh man, I did this wrong. I implemented this the wrong way. Yeah, this is unfortunate. No, this is fine. dj.save. Int effect, I guess let's say int count equals 0. If int parts equals 0. If this, then parts minus minus, essentially n parts. This is very weird. I don't know what's going on here. Okay, so now for each of these positions, we save, int parts save equals parts, dj.restore, parts equals parts save. If we can't ever do this, return false. So if parts equals 1, return true. Otherwise, we need to make it 1 here. So, yeah, okay. If, we care about if their x's are the same or their y's are the same. Well, okay, if dj.find v.id is equal to dj.find o.id, then they're already connected, so this isn't helpful, so just continue. I guess if they're not equal. Here's the important part. Okay, so now, if they're not connected, if v.x equals o.x or v.x or v.y is equal to o.y, then if v.Manhattan distance to O is less than or equal to this distance times 2, then we can merge them. If dj.union v.id to o.id, parts minus minus. Okay, so now if parts is equal to 1, then return true. The other case is if they're orthogonal, in which case things get messy. So int, there are 2 ways of doing it. So yeah, we can, oh my goodness, ugh, it's messy. Okay, so the first way is horizontally from V. Oh, no, because we'll hit the other way when we hit this other loop in the for loop. So this is actually fine. So we just need to go, yeah, go horizontally from V and then vertically from U. So first okay, so if if math.abs of v.x minus o.x is greater than dist, or math.abs of v.y minus o.y is greater than dist, then we can't actually do anything. Otherwise, we can join them. So now we want to do this here. Okay. We also have this new x. So int placed x will be u.x. Int placed y, or u.ox. And these should not be, this needs to be ox and oy. Placed y will be v.oy. Okay. So if v dot ender right and left are 1 and 3, 1 is not equal to null, this, I think. ID -1. Okay, if this thing's in direction 1 is not equal to null, and Manhattan from placed to v dot indir at 1 is less than the distance, less than or equal to the distance, then we can try unioning them. That's just, there's no else, I guess. Same thing for 3. Distance 3. And then we can also go vertically from, yeah, we can also go vertically from O. This part's also wrong. This should be this dot ID. This should be thing in direction 3. This should be direction 0 and 2. This should be, these should both be O. This should be this. Okay. Man, that is messy. I think that's fine though. So if not possible, for all points, the distance will be 2e9 then we print -1, right? So -1. Otherwise, int min will be, let's do long min equals 2e9. Min 0, max will be, do you have to place 1? At most 1, got it. Yeah, I don't think that's a problem. So while min not equal to max, and mid would be min plus max over 2, casted to an int. If possible, points in mid, then do one thing, otherwise do another. So if it's possible, that means that our max might be, well, our max is big enough. So max equals mid, otherwise min equals mid plus 1. And then sys out the min. And the ID is 100. -1. Yes. Okay. Classic. Return. -1. This one is supposed to be 2. And 2 as well. Hmm. Time limit would be annoying. What is the time limit, by the way? 2 seconds. A little tight. Yeah, okay. So I think that's my contest. Yeah, it's my contest for sure.
关门锁被 C 人发现了。
Wait a minute. How is Monaghan ahead of me? I solved the harder problem. I got more points for it. Was he just that much faster? Did I have wrong submits somewhere? I had one wrong submit. These scores seem kind of wacky. I solved a problem that's worth like 700 points more. How am I losing? Oh, I guess because this was multiplied by 2. Because I was slow in this problem and that time difference was multiplied by 2. Yeah, oh well. Okay, so, well, I guess let's spend the next minute trying to think about how to solve this. And then, yeah, if we have a real idea for this, well, I guess we won't be able to code it, but. Yeah, I don't actually know. I don't have time to do it anyway. Like, I wouldn't even be able to write the prime factorization stuff in a minute 30 seconds, to be honest. So, I guess we'll go over solutions then. To all but E. All the problems I solved. Which looks like a lot of problems here. 7 columns of this graph. But yeah, I don't know. For whatever reason today, I thought A and B were vicious. Like, they each took me 10 minutes. That was kind of brutal, in my opinion. But yeah, we'll see. We'll see. Yeah, solution time. 140th place-ish. So not great, not great. But like, yeah, it was, I don't know. It was a cool contest, I guess. It would be better if I could solve E. That's the goal, obviously. I must be missing something stupid. If 500 people are solving a problem, that's a problem that I can solve. Like, I can solve problems. If like things are getting 500 solves, that means I am good enough to be able to solve them. Because I'm definitely, in a Div2 round, if 500 people solve a problem, it's within my range. Like, there's not really a good excuse for not getting it then. But, we'll see. So, yeah. Let's talk about problems? Or talk about solutions. So, I'll just open them all in new tabs. Alright, so problem A, you've got a bunch of digits, and in Valorant. This is a super popular video game. I've never actually played it, but I've heard people like it quite a bit. So, the idea behind the game is that there are a bunch of numbers. So you've got like some digits here. And Alice can take these positions. Bob can take these positions. And Alice, you're gonna keep like imagine, like you just like erase a number, but nothing changes its positions. So like the numbers that you have are fixed, basically. So repeatedly, you're gonna keep doing this. So Alice will delete a number, maybe Bob will delete some number, then Alice deletes one of her numbers, Bob deletes one of hers, and then Alice deletes one of hers. At the end, when you have just one number left, you want one player to try and win. So Alice wants it to be odd, Bob wants it to be even. And then you just say who wins the game. So the first observation to make is we can figure out which set this will be in just by looking at the parity of n. That's easy to do because, for instance, if like, in this case, no matter what Alice picks, it's Bob's choice what the last number is. The last number is either going to be this one, or this one, because Bob gets to choose which two of those three get deleted and which one doesn't. So Bob will pick one of these. So we just need to see in this group of three, is one of them the parity that Bob is looking for? So one of them, if one of them's even, Bob wins. If they're all odd, we know no matter what Alice does and what Bob does, one of these three will be picked. So that means Alice is going to win. And the same thing happens the other way if the parity is the other thing. So if the parity is odd, that means it's one of these three positions that'll get fixed. And you just see, can Alice force a win by leaving one of these that is her preferred parity? Except they use names that weren't Alice and Bob, which made it harder for me to read. But anyway, yeah, here's what it looks like. So if this is odd, then Alice can win, otherwise or Alice can choose who wins, otherwise Bob can choose who wins. Obviously, she can only choose it if there exists a number that she can win with. So that's what this check is for. So that's the idea for problem A. I thought it was a good problem. I didn't mind it. It was interesting. I like game theory problems. I thought that one was good. This one, oh my goodness, this was a mess for me. So you've got, this is annoying to explain, I think. You've got a staircase. You want to see how many perfect staircases are there that have no more than n cells in total. And a staircase is perfect if it has exactly n squares and has height n. So the first thing to notice with that is, since the staircase looks like this, every time you have a square, like you have n different corners here, right? You can only have a top left corner if you have a square that ends here, which means your top left corners are fixed. You have to have a square that looks like this, you have to have one that looks like this, etc. Now, there's more things we can observe from this, which is this square here, it only has height 1, which means it has to end here. Then when we look at this square here, we know this space right here needs to be filled up by some square, which means this needs to be height 2. So this one is height 2, and it goes like this. This one now has to be height 1, because it only has a height of 1 here. This one has to be height whatever this is, which is 4. Yeah, this has to be height 4, because it has to fill in this square here. So this one's height 4. And then you can see, like, the pattern that you have to make is forced. So it has to be height 1, height 2, height 1, height 4, then 1, 2, 1. Now, the total number of squares used will be each of these values squared, because this is just the side length. So it'll be 1 squared, 2 squared, 1 squared, 4 squared, etc. We can look at these values like kind of recursively, because there's this pattern to them. So you've got 1, 2, 1. Then we have this 4. But then we have the 1, 2, 1, which is the same thing, just on the other half. 1, 2, 1 here. So we can take a very big step all at once. We can double the length of this string in order 1. That lets us solve this problem in log time. So, or I guess it's log of square root of n, really. Because these numbers get big, but I guess the log n part is what matters. So, yeah. So let's just say log n for now. I won't worry about the runtime too much, but it's fast. It'll be very, very quick. So yeah, the idea is we just need to keep track of like all of these things at once. So we need to keep track of what is the total number of squares used in this piece, and then what is the next piece we'll add. Then we put this piece twice. That's the idea. So you can imagine this green and yellow part, you have the area of that. Then you place that, place another one, and place a block in the middle. And you can keep track of all of that at once. For code, that looks like this. So what am I doing here? Count is my final answer. And then these two things, this value stores the total number of squares in the bottom left group, and the power stores the size of the next square I'm about to add. So initially you just have a 1 by 1. The next square you're going to add is a 2 by 2. As long as you can keep doing this, then you count this additional square, you use all of these spaces up, and then, wait a minute, am I gonna fail this? Oh, in total, yeah, okay. So yeah, so you use up some of these squares to build this smallest staircase. Then you have to place this thing in the middle. So that's what this is doing. Then the size of the middle doubles for the next time. So that's the idea behind the code here. Okay, for problem C, yeah, this was a cool problem, I thought. Bounds were small maybe in order to be tricky. They could be quite a bit bigger because my solution was linear with almost no overhead. But here's the idea. I guess I won't show it to you. I'll talk about it first. So the first observation is you can always do it in 2 turns. Like, let's look at some examples. So maybe you want the value to be 5. So like target equals 5.
Wrong answer, test 2, sir. Wrong answer, AC1, problem D. Wrong answer, AC1, problem B. Wrong answer, AC1, problem C.
Right. Let's say you want the target to be 5. Your numbers are 3, 4, and 12. Maybe you have like a bunch of other numbers too. What you can do is you can make all of the numbers except for the last one equal to 5, and then just push all of that delta, because you need the total delta to be 0, off to the last person. Now this isn't necessarily actually possible in a real ELO system, but in the simplified version they gave, this is always something you can do. So you can make this 5, and this 12 plus 3, so make this 15. And now you have all of these people sick, except for the last person. Then on the second turn, you can make this person sick by making him 5 and then giving the delta to someone else. So that's the idea. It's always possible in 2 turns. Now we just have to check, is it possible in 1 turn, and is it possible in 0? 0 is really easy. If the target's like, if we're trying to make everything equal to 3, if you get sick if you're equal to 3, then everything just needs to be 3 initially. So that's really easy. Now, the only part of the problem that's left is, can you get everyone sick after only 1 turn? The way to do that is a bit tricky. There are 2 cases. The first is the one they gave in samples. So if you have like 68 and 70, and then you want to reach 69, you can make everyone equal to 69 on the first turn. So here, you can make both of these 69, because the sum of these will be 2 times 69. That's the first case. The second case is if you have like 68 and 70, and then your target is 70, then you already have this person here who is sick, even without doing anything. Which means you can take whatever extra points you need to and give them all to this person. So instead of like having the one person that hits a number that's undesirable in the first turn, you can give all of your extra to this person basically, and that will allow you to get everyone except for this person equal to 70 after this turn. So that will allow you to do it in 1 step as well. Those are the only 2 ways of doing it that I was able to come up with, which I think that's all the ways of doing it. So yeah, code's pretty simple. We just check if they're all equal, and then we check if we have one thing that starts at the weight in which people get sick. That's just that logic, pretty simple. If everything's equal, the answer is 0. If the sum is perfect, or one person starts at the sick value, we can give one person everything, and the rest will just work out. So then it's possible in 1 turn, otherwise it's possible in 2. Cool, that's problem C. Okay, problem D. I'm gonna go over just D2, because D1 is just a simpler version, but it's a bit messy. So the idea is we're gonna sort the numbers, and then after we do this, we just need to be really, really careful with implementation. So here, the sorted numbers look like 1, 2, 2, 3, 4, 4, 5. So the biggest the answer could possibly be for this problem would be, at most, you can have 3 surrounded by 4 other things. So you have like some padding, then you might have your answer, some other padding, your answer, some other padding, your answer, and some padding. You want these to be local minima. So you want each of these to be smaller than the 2 things next to it. That's the goal, I guess. Rearrange this so that that happens. And you want to maximize the number of these that are local minima. Now, like I mentioned, for this case, when you have 7 things, the most local minima you can get is 3. In general, if you have n things, the most you can get is n minus 1 over 2 floored. You can do some examples to prove to yourself this is true. So how do you actually go about doing this? Well, like the first observation we can do is make an exchange argument, like kind of a greedy thing, to say for the elements that will be the local minima, we might as well just have those be a prefix of the final answer. They might as well just be the smallest numbers we can get, because it doesn't help us to have a big number in there. We could just make it smaller and swap those 2, and it would just make the answer better. So we're just going to use some prefix of the easiest numbers. And then for the paddings that matter, we'll use some suffix of the numbers that matter. So we'll use the big numbers as padding and the small numbers as these middle things. Now there are a lot of greedy things you might think to do that aren't totally correct. For instance, you can't just use the biggest padding. You can't use like the 5 here, and then the 1, and then the 4, because then it won't work out. You might have a bunch of 3s in the middle, and you can't use 3s as both the 3 here and the padding for the 3. But you could use those first 3s as padding for like the 1, right? So these 3s might still be valuable, but they're just not valuable to pad around 3s. So yeah, so you have to be careful with that. The idea that I used was, these smaller things are never going to be used as padding. So we'll like ignore them from the set of padding elements, and we'll just put them here. We have this 1, 2, and 2. And now for each of these, we're going to use as many of these prefixes as possible, and we're going to use it greedily. So if we're not going to use this 2, then anything bigger than this 2 or equal to this 2, we're also not going to use. We're only going to use things smaller or equal to the 2 that are like to the left of it in the sorted list. So the idea behind that is, for each one of these things, first we need to place something bigger before it, and then we need to place something after it that's bigger than it. Now we're also going to process the padding in increasing order, which means once we've placed something here, if we have any more padding at all, then we'll be able to place that padding here. So we'll end up getting a point for the 1, since we're processing the padding in increasing order. The idea is, whenever we have this 1, we just need to move this pointer over until we see something that is bigger than the 1. In this case, the 3 is right away. So we can place the 3 here and now get rid of the 3. We'll also imagine getting rid of the 1. Now we have this 2. We want to place something here that's bigger than both the 1 and the 2. We just need to worry about the 2, since we know the 1 is smaller than the 2. And we can place the 4 here right away. So now we've placed the 4 and the 2. Now we're checking out this 4 and this 2 here. Again, the 4 compared to this 2 is small enough, so we can place the 4. Then we place the 4, and then we place the 2. Finally, we're out of elements here, so we just need to place the rest of these padding elements. And we know, since the last number we placed was smaller than this 2, that this 5 will be bigger than the 2. So we get 1 extra point for getting this thing, and then we place the 5 here. So we get these 3 points for each of these. Now, there are a lot of cases. You have to be really careful with this. I'll show you my code here, but you got to be very careful not to miss things, unless there's just an easier way that I didn't think of at all. But yeah, so like you have to be careful. These candidates are just the things that I was talking about, that like the smaller numbers. So first I get a list of those. This extracted is like my extracted answer, and then skipped here is the positions that I didn't use, but I still need to have in my answer because I can't delete elements. So I kind of have like Well, I have 4 cases. It's kind of messy. Initially, I try and find the next pair that I can use where the smaller element is actually smaller than the padding for it. So I keep iterating through elements until that doesn't happen anymore. Once it doesn't happen, there are 3 reasons it could happen. Either I run out of big items to use. I don't want to give examples for all of these because it will take a while, but the idea is, like, let's say I have a 3 here, and then I'm trying to find a padding for the 3, and all I have are 3s left in my array. So if I run out of big items, then I can't have this. That means the thing before this needed to be less than or equal to 2, whatever this was. Because we placed a padding here, and that was bigger, that 3 was bigger than this. So yeah, basically that's it. So the idea is when we place this 3 here, we will make this a local minima. That's why I add 1 to our answer here. Yeah, so that's the idea. Then we need to add all of the candidates that we have left if we run out of big items, because we can't leave anything empty. Another option is if we... Okay, so like we could also run out of both at the same time, in which case we just stop. So anyway, there's that. The next possibility is we might run out of candidates and have big stuff left over. If we run out of candidates, that's fine, because we can just place the big stuff. We know it's big enough because we got through this while loop, and we'll just keep going, right? So we add all the skip stuff, and then we print the answer. The last case is if we actually found something that works, in which case we place both of them and then just keep going. This is sketchy why this happens, but basically the idea is that sometimes you can have candidates that are equal, and then if you put the 2 candidates next to each other, it causes a problem. So yeah, there's that. The example for that, I think, was 1, 2, 2, 1, or I guess, yeah, 1, 1, 2, 2. So in this case, for 1, 1, 2, 2, that's a good test case. You just have this 1 here, so you place the 2 and the 1, and then you end up skipping this 1, and then you skip one of the 2s as well. So you skip this 1 and this 2. And then you want to put these at the end. But you have to put them at the end in the right order, because you skipped this one because you didn't get to it, but you skipped this one because it was too small. So you want to skip the things that are too big first. That way you end up being bigger than the 1. Okay, yeah, so that's it. That's a lot. It's a lot of cases. Basically just like go through all examples of things that are like 3 long, 2 long, 4 long, and 5 long maybe. There aren't that many of them. They're like 30. And then you can just do it on paper, find a break case, and one of those should break you if your solution is clean enough. Yeah, okay, that's the solution to D2, which also works for D1. Okay, problem E. I don't have an idea of how to implement it cleanly. So yeah, I won't spend too much time talking about it, because if there's an editorial out for it, that's probably going to be more helpful than my solution. So I'll leave problem E for now. But problem F I'll talk about. So for problem F, you have a bunch of points on a 2D grid, and you want to join all of the points together. Or I guess I'm kind of spoiling the solution, but you want to, like, yeah, basically you want to find like some tree between all of these points where each, like, you can travel between 2 points only if it's either like straight horizontally or straight vertically. So you could go like this or like this. And then also only if it's less than some t. So like you have this constraint on this edge length. Now you get to choose what this requirement is. You want to make it as small as possible. That's the idea. So the question is, 1, is it possible to make the graph connected by adding these edges? And then 2, if it is, what's the minimum t that you need in order to make it connected? So how do we solve the problem? If you didn't see it, we can binary search this t, and sometimes that's helpful. In this case, we will assume that's helpful, and then we'll move on from there. The reason for that is if you can make the graph connected with t equals 7, then if t equals 8, anything that works with t equals 7 is still viable. Valid and viable. You can use them still, so we will. Cool. So now we have some stuff, and we need to see if it's connected. That's easy enough to do, but there's one extra part of the problem which makes it pretty tricky, and that is you get to add an extra point. So maybe you have something that looks like this here. We can use these edges, that's fine, and maybe this edge is too far away for us to use. But we can add this point here. We can add 1 point, and then that allows us to use this edge, and this edge. So when we add this extra point, we can make something solvable, maybe. And the question is, like, I guess, how do we find this point and do something efficiently? So we're already going to binary search the answer. So you have a log n on our runtime times whatever we can do this check in. Now here's the idea behind this. Every time we add some point, it can do a couple things. So if you have some point here, there are a couple things that could connect. It's possible that it connects these two if they're too far away. So maybe this is the t that we're binary searching, and t is equal to like this length. So we're not able to reach from one point to the other, but we can reach halfway or something. We can reach to this middle point that we want to use, and that will connect them. That's one possibility. The other way it might connect two elements is if they don't like share an x or a y. So if we have like these 2 points here, then we can add this point here, which will connect them. Now, if we don't have the t restriction, there will always be this point. We could always go horizontally from this one and then vertically to the other one, and that'll find the answer. But we do have the t restriction, so we have to make sure the distance we go horizontally and the distance we go vertically are both small enough. So yeah, basically that's it. Now, the idea is we're going to brute force the pair of points that uniquely define this point. If the 2 points are both horizontal, then there are a range of points this could be in the middle. But if they're both horizontal, we won't worry about the vertical connections. Because we'll say if the vertical connections matter, then that's, I guess, easier to work with in some sense, because they uniquely define what this point needs to be. If we are using this point for a horizontal connection, we could use it for the vertical connection as well, and if we're using it for both, then we'll define it in the vertical section. But if we're only using it for horizontal, then it doesn't matter where the point actually is, because it's not being used in any vertical sections, because it's just for horizontal, like I mentioned. So in that case, we won't worry about exactly where to place it. We'll just say, okay, it's going to connect these 2 points. All right, so we have that. There's, I guess, one other thing you need to handle, which is maybe a bit messy, but doable for sure, which is you need to be able to very quickly figure out, if you're going to, quickly, I mean like order 1. Okay, thank you. Please come back. I don't know what happened there. Very quickly figure out if you place a point in some position, what points does that join? So in this case, if we were to place a point here between this point horizontally, this point vertically, will that connect us to any points over here or over here? And we can do that by storing for each point what point is the first to the left, right, up, and down of it. And those are the ones that we need to check. So yeah, because it's possible if we place this, it'll connect these two. And that we have to handle. All right, so that's the idea behind most of the solution path. There's one more part, which I haven't mentioned, and that is how do we actually like worry about these components that are connected? Because we need to measure like what components are connected and how to deal with them. And that's a tricky thing to do. To do that, what we can do is use a restorable disjoint set. And the idea behind this is it's kind of like a persistent array, except everything is order 1. You've got like 2 copies of your array. You've got 1 copy that's like a tentative modification and 1 copy that's the permanent modification. So you've got like permanent joins and tentative joins. And what you can do is you can erase all of the tentative joins at once in order 1. So you can do that with a thing called versioning. You can also do it by storing like a queue of operations and then undoing those, or a queue of operations and then like removing them. But yeah, that's kind of like beside the point. I'll show you the implementation in a bit, but like the idea is this is just a regular disjoint set. So it supports the find operation, it supports union, and then it also supports 2 other operations, which are the restorable parts. So you can save your state, and then you can also restore. Now, you have to do, like, you can only save 1 state. You can't save, like, 2 different states. You can't save, restore, restore. You have to call save, restore, that's it. And that's the idea behind a restorable disjoint set. So what you can do for this is, for all of these permanent changes, where these are just changes that don't matter where we put our special token, all of these we can make before we ever save the restorable disjoint set. Now, when we need to save it, first we can save, and then we can say, okay, let's place this item here, and that'll join these 2 together. So now we can join them. But then when we say, okay, now we've processed this item, it didn't work. If it did work, we just return true. We say, okay, this is possible, continue the binary search. But if it doesn't work, we need to say, okay, we need to undo all of the unions that we've done here. And in order to do that, we can just call restore on this restorable disjoint set. So that will allow us to like massively reduce the casework of saying, okay, well, like, are these 2 in the same component? If they're not, are these in the same component? Blah, blah, blah. Otherwise, like, because like you have to, the counting part gets tricky, and just case working it out would be very difficult. So it's a lot easier to just use this restorable disjoint set data structure to do that for you. Okay, what does the code look like? This part here gets the first point in all 4 directions from each other point in n squared. You can do it better, probably. Yeah, you can definitely do it better, but n squared is fine. So yeah, okay, that's that. Then we just binary search the answer. So that's this part. And I have this possible method, so I can reuse it here. I say if it's not possible, even when you have no constraint on d, or on this distance, so even when the distance can be 2 billion, which is as big as it would ever need to be, if it's still not possible, then the answer is going to be -1, because it won't ever be possible. It won't get better than that. Otherwise, we binary search. We know when it's 0, well, it's not going to be better than 0, right? So we binary search the first or the last time that it is possible from 0 to, or from infinity to 0. And that's that. Okay, so how do you do this possible part? Well, I talked about this earlier, but we look at each of these points. If they, or we look at each point, then we look at each of the closest things in all 4 directions and union them if we can in this disjoint set. This is actually a restorable disjoint set. These are all permanent because we haven't saved yet, so they're all permanent changes to the disjoint set. So then this pair tries all pairs of like defining points that we'll use in order to union other parts of the disjoint set in order to decrease the number of components. I make my union method return true so that if I ever union 2 things, I can subtract 1 from the total number of parts. You can also keep this inside the disjoint set. It's not too hard to maintain, and that works as well. Then instead of just calling this number of components outside, you can just do disjoint set number of components. But yeah, that's kind of beside the point. There are 2 cases here. This first one is if we're only placing this to horizontally connect 2 elements. In that case, we won't worry about the vertical part. The other case is the vertical part, which is more messy. So let's talk about that. I'll move this over here so that you can see it better. Wait, it's not, my face isn't taking up any of the code. But yeah, okay, so if they're too far away, in that case I just kind of skip it. But if they're close enough in both the X and the Y, then I know where I can place this. I don't have to try both positions because I'll try these from, I'll like try UV and then also VU because I'm doing just a naive for loop up here. So yeah, the idea behind this is like, we also need to check if the thing to the right of point U would be unioned. And that is what this is doing. So like if when I go right, this man is just Manhattan distance. If I go in this direction, if the distance from the thing I'm about to place to the thing that was to the right of this is less than the distance, then union these two. That's the idea. So yeah, okay, that's the code. If parts is equal to 1, that means you can put everything in one component, so it's possible. Finally, I save or I restore what the disjoint set looked like before I did all of these operations. Cool. Yeah, that's all of the problems except for E. Hopefully you enjoyed, and I guess let me know what you thought of the contest. I thought A and B were unusually hard. Usually I think they're a little bit easier than this. Oh man, did I fail this? No, I just submitted wrong in contest, so I'm still in queue. Yeah, I think I'm pretty confident in all of my solutions except for maybe D. D is very caseworky, and it's possible I missed something. But I'm pretty confident in the rest of them, I think. So yeah, let me know if you enjoyed the contest. I thought it was pretty good. I thought the problems were all good. Hopefully your rating went up, and thanks for watching. That's all for me. Have a great day, and goodbye.